Hello class, welcome to SciChem. Here we are another session for lecture 4 of chemical kinetics. Before watching this session, make sure that you have already watched lecture 3. So let's start. Let's start with a problem. Let's start with a problem. Here we are. Given rate of certain reaction depends upon concentration according to reaction age. Rate of certain reaction depends on the concentration according to reaction age minus dc by dt is equal to k1c divided by 1 plus k2c. Then determine order and rate of reaction when concentration is very low. 2 points are given and concentration is very. So let's start. What is given here? Let us consider the given minus dc by dt equal to k1c divided by 1 plus k2c. This data is given. Minus dc by dt is the change in concentration that will be equal to k1c divided by 1 plus k2c. Then determine order and rate of reaction when concentration is very low. So let's start with point number 1. Here point number when concentration is very low. When concentration is very low, that means I can say that C tends to 0. C tends to 0. So this is the choice is given, so I can simply write limit C tends to 0 minus dc by dt. Why say C tends to 0? Concentration is very low. I can write here limit C tends to 0 k1c divided by 1 plus k. Age C tends to 0, I can write here k2c tends to 0 and 1 plus k2c equal to 1, approximately equal to 1. So limit C tends to 0 minus dc by dt is equal to k1c, or simply minus dc by dt minus dc by dt equal to k1. This is rate of reaction, this is rate constant k1, and the rate of reaction is equal to k1c. So I can say that this is first order reaction. Why I am writing a first order reaction? Since rate of reaction is equal to rate constant into concentration of power 1. So I can simply write that it is a first order reaction. When first order reaction, when the concentration is very low, then rate of reaction is equal to k1c. So I can simply write that when concentration is very low, that follows first order reaction. Again, the important question is there, and for that is when concentration is very age for that part concentration is very low, so C tends to 0. When concentration is very high, I can say that C tends to infinite. C tends to infinite, or 1 by C tends to 0. C tends to infinite or 1 by C tends to 0. So I can put here limit C tends to infinite or limit C tends to 0 minus dc by dt, sorry, here 1 by C tends to 0. That will be equal to limit 1 by C tends to 0 k1C divided by 1 plus k. Here I can write limit 1 by C tends to 0, dividing both sides by C, I can get here k1 divided by 1 by C plus k2. So 1 by C tends to 0, so I can write here limit 1 by C tends to 0, that will be equal to k1 by, or in other words I can write here when the concentration is very high, or limit C tends to infinite minus dc by dt equal to k1 by, since it is the rate of reaction, it is the rate constant, so rate of reaction is equal to k1 by k2. That means rate of reaction is equal to constant. Since rate of reaction is equal to constant, and it will be a zero order reaction. So for first part, it is first order reaction when the concentration is very low. When the concentration is very high, that is zero order reaction. For concentration is very high, C tends to infinity. As C tends to infinite, then I can say that 1 by C tends to. So this is the problem solving approach for question number 1. Then again another question is there here. For a reaction 2A plus B gives rise to product. For this reaction, I have rate of reaction R1 is equal to K into A power 2 and B power 1. And for the reaction 4A plus 2B gives rise to product, I can write here R2 is equal to K2 A power X B power Y. Then derive the relationship between K1 and K2, much more important, and determine the value of X and Y. This question. Two A plus B gives rise to product. For this reaction, I can write here R1 is equal to K into A power 2, or I can write here R1 is equal to, for that reaction, 1 by 2 of minus dA by dt, rate of reaction. By comparing rate of reaction R1, I can write here 1 by 2 minus dA by dt is equal to K into A power 2 B power 1, or minus dA by dt is equal to 2K A power 2 and B power 1. Again given here, and this reaction, watch here, this reaction is multiplied by 2, so I can write here 4A plus 2B gives rise to product. So for that reaction, here R2 is given K2 into A power X B power Y, and that will be equal to R2 is equal to 1 by 4 of minus dA by dt, or I can simply say that by comparing R2, 1 by 4 minus dA by dt is equal to k into a to power x b to power y, or minus dA by dt is equal to 4k a to power x or y. So consider this is equation 1 and this is equation. So by comparing equation 1 and 2, I can say that by considering equation 1 and 2, I can say that 2k a to power 2 b to power 1 equal to 4k. Sorry, I make a mistake. Rate constant is given here. Consider k1. That is asking what is the relation between k1 k2. There is a mistake, sorry. Is k1 a to power 2 b to power 1 and k2 a to power x b to power y. There is a mistake. So I can write here by comparing equation 1 and 2, 2k1 a to power 2 b to power 1 is equal to 4k2 a to power x b to power y. So I can write here I can write here 2k1 is equal to 4k2. How I can write here 2k1 is equal to 4k2? Because we have already studied some important examples or different value of order in the rate law expression, that on changing stoichiometry here, what happens, 2a plus b gives rise to product, and here by multiplying this we have 4a plus 2b gives rise to product. On changing stoichiometry of the reaction, rate of reaction will change, rate constant will change, but order will not change. On changing stoichiometry, rate of reaction will change, rate constant will change, but order will not change. Here for this reaction, order is 2 with respect to A and 1 with respect to B. So similarly, for the value xy, x is equal to 2 and y is equal to 1. So here if I put x is equal to 2 and y is equal to 1, by cancelling this I can get 2k1 is equal to 4k2. So k1 is equal to 2k. This is the relation between two rate constant. K1 is rate constant for first reaction and K2 is rate constant for second reaction by changing stoichiometry. Again I am reading this question. 2a plus b gives rise to product for this reaction given R1 is equal to, it is K1 a to power 2 b to power 1, and for the reaction 4a plus 2b gives rise to product R2 is equal to K2 into a to power x b to power y. So for two reaction, two rate constants, two rate of reactions are given with rate constant K1 and K2. Then derive the relation between K1 and K2, which I have already calculated. K1 is equal to 2K2, and for determining value of x and y, I got value of x is equal to 2, y is equal to 1. There is not much difficulty, but simply remain on changing stoichiometry of the reaction, rate of reaction and rate constant changes, but the order does not change. If you don't remember, I can show you here. This on changing stoichiometry, the rate of reaction and rate constant changes, but order does not. Remember this part. On changing stoichiometry, the rate of reaction, rate constant changes, but order does not. So here by changing stoichiometry. Here I have put same value of order. X is equal to 2, that is order with respect to A, and Y is equal to 1, that is order with respect to B. So these are the two problems. Next, come to next part, that is zero order kinetics. So what are zero order kinetics? What are zero order kinetics? The reaction whose rate does not depend upon concentration and time are known as zero order reactions. The reaction whose rate does not depend upon concentration and time are known as zero order reactions. So let us consider a reaction A gives rise to product when time t is equal to 0, initial concentration is A naught and the product is 0 from 0 amount, and when t is equal to t, after some time the concentration left will be A naught minus x and x. For A naught minus x I can write here, for A naught minus x I can write here, this is AT and it is BT, where AT is, where AT is equal to A naught minus x. That means AT is concentration left after time t, and BT is equal to x. That means concentration left after time t for product. X amount of product will be formed. So let's solve zero order kinetics. For this reaction I can write here rate R is equal to change in concentration minus dA by dt is equal to K power 0. Why 0? As it is a zero order reaction. So I can simply write here minus dA by dt is equal to K. Or minus dA by dt is equal to K by what is change in concentration. For minus dA by dt, here I can put here minus d by dt is equal to final minus initial concentration. What is the final concentration of A? That is A naught minus x minus A naught is equal to, and that will be equal to minus plus dx by dt. That is left minus x and minus d by dt, so that is plus dx by dt is equal to, so dx by dt is equal to K. This is differential zero order form, and this is considered equation 1. So we have dx by dt is equal to K by integrating both sides, taking suitable limits. I can write here dx is equal to k dt, dx is equal to k dt integrating. For integration I can put here dx is equal to 0 to x and it is 0 to t. Why it is 0? At time t is equal to 0, the concentration of x is 0, here x is 0, and at time t is equal to t, the maximum concentration of B is formed, that will be equal to x. So at time t is equal to 0, the concentration lower limit is 0, and at time t is equal to 0, maximum concentration is x. So by solving this I can get here integration of dx, I can put here x 0 to x equal to k t 0 to, by solving this I can get x is equal to k is equation 2. X is equal to kt. So concentration of A after time, that will be equal to, we have AT is equal to A naught minus x. So I can simply put here AT is equal to A naught minus KT. A naught minus KT. This is AT, concentration left after time t. And similarly, concentration of B after time, we have Bt is equal to x and that will be equal to Kt. Consider this is equation 3 and this is equation 4. So next part is there, we have to calculate lifetime of zero order reaction. Lifetime of zero order reaction means time period in which in which 100% of reaction gets completed. I can denote lifetime of the reaction as TLT. So lifetime of zero order reaction, what is the time required to complete 100% of the reaction? So I can simply say that at TLT 100% completion of reaction means there is zero amount of concentration of reactant will be left. So I can say that 100% of reaction when gets completed, 100% of reaction, the concentration of A will be 0 or AT is equal to 0. Concentration of left after time t, AT is equal to 0. So I can simply put here at TLT, or sorry, at time is equal to TLT, at time t is equal to TLT, I can write here AT is equal to 0. From equation 3, AT is equal to A naught minus KT. So AT is equal to A naught minus KT. As AT is equal to 0, I have A naught minus KT is equal to 0, or A naught is equal to KT, or sorry, A naught minus TLT. Why TLT? When AT is equal to 0, I have T is equal to TLT. So A naught is equal to KT. So TLT is equal to naught by K. Why I have put here TLT? When T is equal to TLT, then AT is equal to A naught. This equation AT is equal to A naught minus KTLT. At KTLT, AT is equal to 0. So 0 is equal to A naught minus KTLT, and A naught is equal to KTLT. So TLT is equal to A naught by, this is the lifetime of the zero order reaction. That means A naught by K is the time period during which the reaction gets 100% completed. Similarly, we have to calculate half-life, that will be T half. Similarly, I can say that for a lifetime, time period in which 100% of reaction gets completed, so I can write here time period in which 50% of reaction gets completed. So I can simply say that at a t is equal to t half, then at is equal to a naught by 2. 50% of reaction gets completed means 50% of the reactant will be gets completed. So at a t is equal to t half, I can write here at is equal to a naught by 2. Similarly, from equation 3, I have at is equal to a naught minus kt, and value of at is equal to a naught by 2, that will equal to a naught minus kt. So kt is equal to a naught by 2, it is t half, t half, t half, and t half is equal to a naught by 2k, and this is half life. From this I can get a conclusion. Let us consider reaction 0 to 100. In the midway it is 50%. In order to complete 0 to 50%, that is half life, I have time required, that is a naught by 2k. For 100% completion of the reaction, I have time period a naught by k. A naught by k. For 100% of the 100% completion of the reaction, I require time, that is a naught by k. For 50% of the reaction, I require time, that is a naught by 2k. So for another 50%, that is 50 to 100, I can write here, that is also required naught by 2k. That means equal amount of reaction will get completed in equal time. This is the unique property of zero order reaction. That means equal amount of the reaction will get completed in the same time or equal time. So this is all about zero order kinetics. So what is zero order reaction? The reaction whose rate does not depend upon concentration time are known as zero order reaction. For this reaction, it can ask what is the concentration left after time t for reactant A. For reactant A, concentration left after time t, that will be At is equal to a naught minus kt, and Bt is equal to kt, that is concentration of B after time t. TLT will be a naught by k, and T half or half life will be a naught by 2k. TLT and T half, by considering these two equations, I can say that equal amount of the reaction will get completed in equal time interval. So what are the examples of zero order reaction? What are the examples of zero order reaction? I can write here the reaction H2 plus Cl2 in the presence of H nu, that will be equal to 2HCl. Where I can write the rate of reaction K is equal to H2 power 0 Cl2 power 0. Next, another example I can draw. All enzyme catalytic reaction. These are the example of zero order reaction. Next, I can write here dissociation of gas. Dissociation of gas on solid surface are examples of zero order reaction. Then graphs related to zero order reaction. What are the graphs related to zero order reaction? Graph to order. First graph is rate versus concentration. The rate versus concentration, since rate is independent of concentration, I can say that R is equal to K. Similarly, rate versus time, is same equal to K. Age, this is zero order reaction. Rate is independent of concentration and independent of time. So R is equal. These are the graph. Next, what is the graph between AT? We have AT is equal to A naught minus KT. Y is equal to mx minus mx plus c. So this is the equation of straight line having intercept A naught and the slope will be negative slope. Another graph is there, that is concentration of product versus time. Since the concentration of reactant decrease with the progress of time, similarly concentration of product we have x is equal to kt, or that is bt equal to kt. This is bt. It is linearly decreasing here. Here the product is linearly increasing with a positive slope. Then what is the graph between T half and right here T half is equal to by T half is equal to 8 k into y is equal to right. This is the equation of. So these are the graphs related to zero order reaction. This is rate versus concentration. This is rate versus time. This is concentration of reactant and time. This is concentration of product with respect to time. This is half-life time with respect to A. Some important characteristics of zero order reaction are equal amount of reaction completed in same time. As I have already told you, let us consider a reaction 0 to 100. If 0 to 50% required A naught by 2k and 0 to 100 requires A naught by k, so another 50% will also be get completed in A naught by 2k. This means equal amount of reaction gets completed in same time. So if 100 to 90, that means 10 unit will be utilized in 10 minutes, then 90 to 80 another 10 when we utilize it in 10 minutes, then 80 to 70, that means another 10 unit also utilized or consumed in 10 minutes. So equal amount of reaction will gets completed in same time. This is the unique property of zero order reaction. Next part is concentration of reactant left after equal time interval are in AP. AP means arithmetic progression. I can say that when time t is equal to 0, I have A naught, initial concentration. When time t is equal to t, I have value A naught minus kt. When time t is equal to 2t, I have value A naught minus 2kt. When time t is equal to 3t, I have value A naught minus 3kt. So in between these two we have difference of kt, kt, kt. So this is arithmetic progression. Concentration of reactant left after equal time interval are in AP. This is arithmetic progression. Next part is there, half lifetime depends on initial concentration. So T half is T half directly proportional to naught by 2k. So T half is directly proportional to initial concentration. So this is all regarding zero order kinetics. Thank you for watching this